So what is cache locality and why does it matter in memory management? Let's break it down step by step. In modern computer systems, memory is organized in a hierarchy. At the top, you have the fastest memory, the CPU registers and caches. Then you have the RAM, and finally, disk storage. The closer you are to the CPU, the faster the memory access. But also the smaller and more expensive the memory is. Now, the CPU cache plays a critical role in performance. It stores small chunks of memory that the CPU is likely to access soon. This is where cache locality comes into play. There are two types of cache locality: temporal and spatial. Temporal locality means that if a piece of data is accessed once, it's likely to be accessed again soon. Spatial locality means that if a piece of data is accessed, nearby data will likely be accessed soon too. Let's see a C++ example to make this clearer. Suppose we have two loops that do the same logical operation but access memory differently. This code has good spatial locality. Why? Because C++ stores 2D arrays in row major order, meaning matrix ij and matrix ij+1 are next to each other in memory. So when we move across columns inside a row, we are accessing contiguous memory. Compare that with this. This time we are jumping across rows for every column. So we are accessing memory in a way that breaks spatial locality. Even though we are doing the same computation, this version will be slower because of more cache misses. Cache misses happen when the data the CPU needs isn't in the cache, so it has to go fetch it from main memory. That's hundreds of cycles slower. Good cache locality reduces cache misses and boosts performance significantly, especially in large data processing tasks. Another common scenario is with structs and classes in C++. Consider this example. If we loop over the particles array and update positions and velocities, we will benefit from spatial locality, because each particle is stored contiguously in memory. But let's say we change the design and do this instead. This is called a structure of arrays versus the previous array of structures. Depending on what operations we are doing, structure of arrays can be more cache friendly. For example, if we are only updating velocities. In this case, all access data is packed together in one array, improving cache efficiency. With array of structures, we would be skipping over x, y, and z to get to each velocity, which may cause more cache misses. So designing data structures with cache locality in mind can make a huge difference. Another thing to consider is memory alignment. Misaligned data can span multiple cache lines and hurt performance. Modern compilers and CPUs can sometimes fix this, but you can also use alignment attributes in C++ like this. This ensures the struct starts at a 64-byte boundary, which matches common cache line sizes. To wrap it up, cache locality is about accessing memory in a way that makes the most of the fast CPU caches. It's all about how your data is laid out and how you access it. By being cache conscious in your code, like choosing the right loop order, struct layout, and memory access pattern, you can write much faster, more efficient C++ programs. Thanks for watching.